In this lesson, we will be talking about permutations and combinations. The first part has the definitions of those. A permutation, it says here, is an ordered arrangement of objects. So the main thing you want to take from this is that order matters for a permutation. An example of that would be the seating chart we have in class. I care that you're in a certain spot because that's how I take attendance, or if we would have a sub, they care where you're sitting. And so your spot in that classroom matters. If you just sat wherever you wanted, it'd be hard to take attendance. So I have a permutation for seating charts. So that means order matters. In a combination, it's an unordered arrangement, so order doesn't matter. An example of where order doesn't matter would be someone saying, well, I want to have 4 kids, but I want one of each. I for sure want a boy and a girl somehow. They don't care when they get their boy or girl. They would just like to have one at some point. There's an example of where order wouldn't matter. So here we're just going to kind of get used to whether or not order matters in different situations. So in these situations, we're going to decide if order matters or not. Letter A, your teacher tells you to answer 4 of 6 questions on an essay exam. This can happen to you in different classes when you have a test and they're going to give you 6 questions. They say choose 4. Does it matter the order in which you answer those essay questions? Or which one you do first, second, or third? I would say no, it doesn't matter, right? Order does not matter, so this would be an example of a combination. Number 2, choose 5 of 8 people to sit in assigned seats at a concert. The key word here is assigned seats. Not sit in seats, but they're assigned seats. So that tells me that order does matter. So that would be an example of a permutation. The next one you have is you choose 4 of 20 people to serve on a subcommittee. If I'm choosing committee members, I don't really care who I pick first or not because the committee is just all kind of the same. They each have 1 equal vote. And so we're going to say order doesn't matter here. So that's a combination. Letter D says choose 4 of 20 people to serve as the officers of a committee. Officers would be like president, vice president, secretary, treasurer. Does it matter who your president is versus your treasurer? Probably, right? It'd be a lot different to say, like some people maybe wouldn't have voted for our current president if the vice president would have been the person who was the president. That's how it works. You know, the president is supposed to be the higher up. So you care who that person is. So in that case, order would matter. Hopefully that's starting to make sense which order it goes. The last 2 we're going to look at are choose 3 people in a class of 25 to receive a Hershey Kiss. Since everyone's getting a Hershey Kiss, it doesn't matter the order I hand them out, so that'd be a combination. Choose 3 people in a class of 25. 1 will receive a Hershey Kiss, 1 will receive a Snickers, and 1 will receive a Kit Kat. Since it makes it sound like the first one I choose is going to get the Hershey Kiss, and the second one will get the Snickers, order would matter. Or think of if I had some candy, if I had those 3 pieces of candy up here and I chose your name first, you might care that you were first because you actually now get a choice between all 3 candies. The person I pick third just gets the leftovers. They'd have to take whatever was left over in this case. So that's going to be an example of a permutation. You would care about the order when you get to pick the candy. So now to apply this, hopefully you see in your notes on the very top where it says, after our definitions of permutation and combination, it says on calculator. And that would be how we're going to do some of these. So we'll use our calculator for these when we can. This problem, first though, you always want to ask yourself if it's a combination or a permutation. So it says Susie has 7 different scents of lotion that she is going to place in a row on a shelf. How many ways can this be done? So all 7 will be placed. Order matter? Well, since there's 7 different scents, order would matter because if I have like the raspberry and then the vanilla and then the spice, I don't know what kind of lotions there are. That order matters because these are different from each other. They're not the same thing. So we're going to say this is a permutation. And then it says all 7 will be placed. So here's what you're doing. When you do a permutation, you're going to use the P, and this number here is your total number, and the number here is how many you're choosing. So for this problem, I'm doing a permutation. I have 7 total lotions, and I'm placing all 7. So we're going to do 7 choose 7 as a permutation. So on my calculator, I go to 7, and then so I have to punch the 7 in first, and then I go to math, and I go over to probability, and you can see number 2 there. It says NPR, so I'm going to choose number 2 for that's a permutation. Now the combination then would be number 3. So number 2, NPR, and then I'm choosing 7. So when I hit enter, that tells me all the different combinations. So there's 5,040 different ways that I could have that she could display those lotions. And that's when order matters. In B, it says only 4 of the 7 will be placed. So we still have 7 we're choosing, but we're only picking 4 this time. So on my calculator, I say 7, and then I go over and do NPR again, and I'm picking 4 of them. So I hit 4 here, and when I hit enter, we get 840. So there are 840 ways that those lotions could be placed. The last one says she wants raspberry and vanilla on either end. This one's a little bit more complicated. So you think of all 7. She's got the raspberry has to be here for sure. So I don't care which end raspberry's on. So my choice for this spot right here is raspberry or vanilla. So how many choices do I have for that spot? I have 2 choices. Now, since they have to be on either end, if I put the raspberry in this spot or the vanilla, how many choices do I have for this spot? Just 1. So I have 2 choices at the beginning, and then when I choose to put the raspberry or the vanilla there, I only have 1 choice for this last spot. It has to be the one I didn't choose between raspberry and vanilla. Now, for all the other spots, it doesn't give us any rules. So how many choices do I have for this spot right here? Well, there's 7 lotions. I just took out the raspberry and the vanilla, so I have 5 choices left. So I have 5 choices for this spot, which means I have how many choices for the next spot? 4, and 3, and 2, and then 1 left over. So we're looking at our choice. Now this is how I'm laying this out. You don't have to show this work, but I'm just kind of hoping you can see why we'd have these choices here. I had 2 choices at the beginning because they only gave me 2 for the ends, and then there were 5 lotions left. So once I place a lotion here, whichever one I pick, there's 4 left for this spot. Then I put 1 in the 4th spot, and then there's 3 left for this spot. So now another way to write this would be I had 2 choices in the beginning, and then I had 5 choices. And so I would take 2 factorial times 5 factorial. What factorial is, 5 factorial is really 5 times 4 times 3 times 2 times 1. So in all these spots, I'm multiplying. And I can do that either way. I can go on my calculator and just punch in 2 times 5 times 4 times 3 times 2 times 1 times 1. Or I can do 2 factorial times 5 factorial. I'm going to show you that just so you can see it. So 2 factorial, and the factorial you'll see is this number 4, that exclamation point. And then I'm going to go times 5 factorial. Oops, I picked the wrong one, sorry. Let's delete that. I meant to pick 4, not 5. There we go. And when I hit enter, I get 240. And you would have gotten the same answer had you just multiplied all these numbers out. So there are 240 ways she could place those lotions, assuming she wanted a raspberry and vanilla on either end. So now number 3, your boss has told you that you need to work 3 days next week. How many ways can this be done? Do you think your boss cares which 3 days you work based on how they worded this? I'm going to say no. Your boss just said you had to pick 3 days to work. So we'll assume that the weekends are in on this since they didn't say you only work 5 days a week. It's not Monday through Friday. They didn't say anything about that. So I'm going to assume you have all 7 days. This would be an example of a combination. It doesn't matter which 3 days you pick. The order in which you pick them doesn't matter as long as you have 3 days picked. So we're going to say we have 7 to choose from, 7 days of the week. This is a combination, and we have to choose 3 days. So I go to my calculator, and I'm going to punch in 7, and then I go and find the number 3 now, because I'm doing a combination, and then I'm picking 3 days that week. So I hit 3, and when I hit enter, I have 35 choices of how to pick which days I'm going to work. There are 35 ways I can choose those 3 days of the week. Now, if they would have told us that that was only out of the 5 days, like Monday through Friday, then we would have done 5C3, and we'd have less ways to choose. Number 4, it says you need to choose 4 of 7 items from column A, 3 of 8 items from column B, and 2 of 5 items from column C. How many ways can this be done? So the first one, I'm going to say that they didn't say anything about order here, so I'm assuming this is a combination problem, the way they worded it. So when they say 4 of 7 items, that means I'm going to do 7C4. And then that's just column A, right? Here's column A. For column B, I have to choose 3 of 8 items. So there's 8 total. I have to choose 3. And for column C, there's 2 of 5. So I have 5 total, and I have to choose 2. So to do this, you actually multiply each number of options for each column. So on my calculator, I'm going to go in and I'm going to say, okay, 7C4 times 8C3 times 5C2. So I put all those in, and I get 19,600 choices. So that's all the different ways I could make those combinations. I have 19,600. When you look at the back, another way that they'll often do order is you need to arrange the letters in the word almond. How many ways can this be done? And so when I'm looking at this word, I have to first make sure that there's no repeats in letters. In the word almond, there's not 2 N's or 2 L's or something that repeats twice, because that would change my problem. Since there's not, I look at the order for a word. Does it matter the order where the letters are for a word when I rearrange something? I'm going to say yes, right? That does matter. So this is a permutation. I have a total of 6 letters in the word almond. So 6P, and how many ways am I doing this? I'm choosing 6 letters, right? They didn't say to make smaller words, just rearranging all these words or letters were given. So I have a 6P6. When I go to my calculator, I'm going to go 6, math, probability. I pick P, make sure you always look at that, and then I'm choosing 6. So I have 720 ways that I could rearrange the word almond. Now we get to the next one, and these are kind of right off your objectives. The next word they want me to arrange is trigonometry. How many ways can this be done? First of all, I have 4, 8, 12 letters in trigonometry. So there's 12 letters. And again, this is a permutation, right? I do have some repeats, though. I have the letter R that repeats twice. So I have repeats. I'm going to mark these down. R, there's 2 of them. So 2 R's. And I have T. So 2 T's. And then I also have 2 O's. So what happens here is when I'm doing the 12 letters, I have 12 choices for the first spot. So it's really the same as 12 factorial. I have 12 choices, then 11, then 10, then 9, then 8. What you have to do, though, is divide by the repeats. So since there were 2 R's, I'm going to divide by 2 factorial. There's 2 T's, divide by 2 factorial, and there's 2 O's. So I divide by 2 factorial. So if I punch this in my calculator, I'm going to say 12 factorial and I get an oops, I must have not hit 12. Let's try that again. 12, and then we'll go factorial, and I hit enter, and then I'm going to divide this by 2 factorial, 2 factorial, 2 factorial. So I'm going to divide by, and I'll go parenthesis, and I could do, well, I'll just do 2 factorial every time. 2 factorial, though, hopefully you realize it's just the number 2, because 2 times 1 is 2, but I'll put them in the way we wrote it just to be safe. So you can see how to do that in case it'd be like a 3 factorial sometime. You'd have to be able to do it this way probably. So I do that, and I'm going to close that parenthesis, and then when I hit enter, I get 59,875,200 ways that I could rearrange the word trigonometry. A lot of options, right? So now we'll keep going. Number 7, it says, in straight poker, a 5-card hand is dealt from a standard deck of 52 cards. How many different straight poker hands are possible? So a straight poker hand would be when they're dealt out, you get numbers that go in a row, right? And so it says that we're looking for a 5-card hand. So when they choose 5 cards, how many straight pokers are given? So I have 52 cards. Would order matter when they hand them out? When they hand the cards out, order doesn't matter, right? It's just when I put them in my hands I would care about the order. So we're going to call this a combination. And so I have a big C. How many cards do I have to choose from in the beginning? In the beginning, I have 52 cards. And then when they just hand out 5 cards to me, how many different combinations are there? I'm taking 5. So 52, choose 5. When I do that on my calculator, I'm going to go 52, and I'm going to do choose, so C, and then 5. And you see that there are 2,598,960 options for when you're dealt 5 cards in poker. Alright, almost there. Number 8. A debate team consists of 3 historians, 4 economists, and 2 political scientists. They need to be seated in a row. How many ways can this be done if? So for A, it doesn't matter who sits next to who. Now, I think the way they word A, it makes you think it might be a combination. They make you sound like order doesn't matter. But when you're being seated somewhere, order always matters because you are assigned that seat. So this is still a permutation. They're just saying of the, how many people do we have here? We have 9 people total, right? So 9 total. Of the 9 people, we don't care the order, or we're having all 9, or sorry, we do care the order, but we don't care who sits next to who. So we're going to seat all 9. So we're just doing 9P9. Punch that in my calculator. And I get 362,880. So that's all the different ways I could seat these people in the debate. Now maybe there's a certain way that the debate team wants to sit so they can help each other out and they can talk easier or whatever the reason would be. So in letter B it says a historian has to be seated on either end. So let's think of these 9 choices they have for where people sit. Here's the 5, 6, 7, 8, 9 seats. I need a historian on either end. So because I'm talking about the historians, we have 3 historians. So how many choices do I have for this end? I have 3 people that could sit here. So when I take one of the historians away and they sit here, how many historians do I have left to choose from for this spot? I still have 2 historians to choose from. Then I have those 2 people seated. So of my 9 people, I've sat 2, so I have 7 left to seat. So in my other order, I would have 7 people to choose for this spot, and then 6, 5, 4, 3, 2, 1. So really, if I want to write this a little shorter, I have 3 choices for the ends, 3 factorial, and then there would be 7 people, because I sat 2 people, left over. So I'd do 3 factorial times 7 factorial. So when I do that, I'll do that on my calculator. 3 factorial times 7 factorial. And I end up with 30,240 ways to seat them. So there's all the different ways I could seat those people using that. The last one says then, if those in the same field must sit next to each other. So again, let's draw out our 9 spaces. It doesn't matter who goes first, and so we're just going to start with the historians because they're listed first. So my 3 historians are going to sit right here, and then next I have 4 economists, so we'll put them here. And then lastly I have the 2 political science. So of my 3 historians, for this spot right here, how many choices do I have? I have 3, right? And then for this spot I have 2, this spot I have 1. So hopefully you see that that's 3 factorial. And then when I come here, I have 4 to sit in here for the economist. So I'm going to say 4 choices here, and 3, and 2, and 1, otherwise known as 4 factorial. And then for my political scientists, I have 2 choices for this spot and 1 choice here. So 2 factorial. The tricky part here, though, is that when I randomly assigned my historians first, then my economists, and then my political science people, couldn't they be in another order? Couldn't this be the first 4 be economists, and then history, and then political science? Or maybe it could be political science and economists and history, political science, history, economists. I mean, there's lots of combinations here I could do. How many combinations? Well, for who goes in this spot, So let me erase this. I initially did start with my historians, my economists, and my political science. But who should go first between those three groups? I could choose, I have three choices between historians, political scientists, and economists first. Then I have two choices, then I have one choice. So deciding which group starts the seating, I have 3 factorial. So that actually has to be up here. I have to take all this times 3 factorial to account for the fact that I could have put in my economist first. And that's the tricky part of that problem, I would say. So if I go to my calculator, I'm going to have to do 3 factorial times 4 factorial times 2 factorial times now 3 factorial. Then when I hit enter, I get 1728. So I have 1,728 ways I could seat so that they are sitting in the same field. Last ones we're going to talk about are license plates. It says the license plate consists of 3 numbers followed by 3 letters. How many different plates are possible if, for A, repetition is okay? So what we're going to do here is we're going to draw out our license plate. And remember, we multiply these, right? So if I can repeat, how many choices, these are our numbers, and these are our letters. How many choices do I have for numbers in my first spot right here? How many different numbers can I put here? Well, I'm assuming they use the numbers 0 through 9, right? Single digits and zeros count. So there's actually 10 choices here, 0 through 9. Which means there's 10 choices here and 10 choices here. Because I can have a license plate like 777. Those numbers can be repeated. So I have 10 choices for each spot. As far as letters, they haven't told us any letters are off limits. So I have 26 choices for each spot here for letters. So I literally just multiply 10 times 10 times 10 times 26 times 26 times 26. And I would find that if letter repeats don't matter, these are all my combinations for license plates. Now think about that for the state of Minnesota. We have probably 20 million, I'm trying to think of our last census. I want to say we're over 20 million people in our state. So do we not have enough license plates for everyone in our state? Except that what's true about maybe half of our state, or 40% of our state, or 30% of our state, whatever it would be. We're going to say they're not drivers, right? Like in my family, there's 4 people, but I have 2 non-drivers, so they don't have their own vehicle. There will be some people with 2 vehicles, but that's how many options we have for license plates if we use a license plate with 3 numbers and 3 letters. So then, you know, what they can do too is you might notice that some license plates in the state have numbers first and then letters, and some have letters and then numbers. So that's a whole nother combination they could do and get 17 more million. So now it says repetition is not permitted. So I can't use the same number twice and I can't use the same letter twice. So I still have 6 spots. For my numbers, I have 10 numbers to use here. And then whatever number I chose, like let's say the number 3 happened to be in this spot. How many choices do I have for this spot now? Well, since 3 is out of the mix, I only have 9 more choices. And then let's say I got the number 8 here. Well, since 3 and 8 are out of the mix, how many numbers are left? 8 more numbers. So that's the number of choices I have. Not the actual number, but how many choices I have for that spot. So the same is true for letters. I have 26 choices right away, but when you take one of those letters out, I now have 25 choices, and then I have 24 choices. So when I multiply those numbers all together, I end up with 11,232,000. So we end up with about 6 million less options if we don't allow repeats on letters and numbers. Which in our state they do allow repeats, because hopefully you've seen vehicles that have double numbers or double letters. And then C, the last one, it says the first letter must be a vowel and the first number cannot be 0. No repeats are allowed. So let's think about this. Still 6. The first letter must be a vowel. So here I'm going to just go with that condition. My vowels, we'll say, are A, E, I, O, U. We can debate why, but I'm going to go with a no here. I'm going to call Y a constant in this case. So we have 5 choices for our first letter. Then, does it say anything else about letters? The first number cannot be 0. So I've taken care of this right here. The first number can't be 0, so that means it has to be numbers 1 through 9. So I only have 9 choices here. There are no repeats allowed. So, I had 9 choices here, but now I can have 0 in this mix, can't I? So I would think I have 8 choices here, but remember we have one more choice in 0. I have the numbers, let's just pretend this number that came out first was like the number 1, okay? I'd have 0, 2, 3, 4, 5, 6, 7, 8, 9. So I still have 9 choices there. And then when that number comes out, now I'm down to 8 choices. With my letters, I would have 26 choices, except I already took a vowel out. So now I'm down to 25 choices. And then when I take out that next letter, I'm down to 24 choices. This would be used, there's a combination here. If you don't know about Minnesota, we have something called whiskey plates. And if you get too many DUIs, you end up having in your vehicle, you have to have a W as your first letter, because then the cops know that you are a whiskey plate and they watch you more closely for driving under the influence. So that's an example of a combination that would be different because we pulled W's out for the first, so we end up with less options. But in this case, I said vowels. So when we multiply these out now, this kind of limits us quite a bit, actually. Look at the license plates here. We only have a little over almost 2 million choices, which I would say in Minnesota we have more than 2 million drivers. So that was not something that would work in Minnesota if we wanted to have vowels go first. Hopefully that makes sense to you. I think once you get through your worksheet and your notes, you'll be good to go on this, I hope.